So welcome back from the very quick coffee break. While I'm finding the file, I would like to start the second block of this workshop, where we named Research and Innovation Contributes. And this is dedicated to the projects that are here, basically, not only the research ones, but also the industrial ones. And I would like to start actually with the project RESQTOOL. That's the one that is organizing this workshop. For that, we have here Jakub Szałatkiewicz from Phoenix, who will talk to us about this project. Just one prayer for everyone who is going to speak. We have really limited time for this section, so we need to stick within the 10 minutes that we have been given. So please, let's try to do that. I'm sure you will. And yes, Jakub, if you can come to the stage, we can start. Thank you.
Thank you, Bruno. I've got the microphone, okay, great.
And you have the remote.
Perfect. Thank you. Hello, I'm Jakub Szałatkiewicz, as Bruno introduced me. I'm presenting our project RESQTOOL, which is related or takes care of the end-of-life hard metal tools, which contain the critical raw materials, mostly tungsten carbides, which is very important. It's not like only tungsten is important, but the form in which the materials are also occurring, because it's a loss to like a downsizing of the materials which are already in the given form. So we've got here the the whole spectrum of the industry in our project. We have next to the manufacturers, big manufacturers of hard metal tools, also the scientific community. We've got companies and the whole spectrum of the value chain. So what are the hard metals? What is the subject of the project? So we are taking care of the tools which are used for metal cutting, for rock drilling, wood cutting tools. There is a lot of various parts, cold forming and other materials which are sandblasting nozzles, which has to be very, very hard to sustain the wear off of the applications. So normal materials doesn't last too long, and very specific like a tungsten carbide, titanium carbide, or other tantalum carbide can only be used to achieve such a let's say life expectations of the tools. As I mentioned, we have in the project the whole spectrum of the let's say value chain. We've got scientific community like a Fraunhofer, CEIT. We have the tools manufacturers, CEIT group, which is also the collector of the hard metal scraps, which is very important. We have to look on the value chain, also on the scraps collection, because it's not only to process the scraps which are already bought from somewhere, but we have to also collect the scraps. If we're not collecting the scraps, there is nothing to process, and then we don't have anything to reuse. So this is very important. And currently, it's a case in every industry, like with magnets, as you mentioned before, and also with those tools that somebody is just looking at this tool. Oh, it's magnetic. Okay, just chuck it into the steels, yeah, and then it goes to waste. And that's what we have to look on. So we have Stadler, who's collecting the scraps from the around, and I'm representing Phoenix Surowce, which is Phoenix Resources, who is responsible for developing the sorting systems of the scraps. And we have also other scientific community, for instance, Unica, which is developing the chemical processing of hard metal scraps for, let's say, green recycling processes. And we've got also the Irish manufacturing research, who was doing the LCAs. As I mentioned a bit before, we are focusing on the scraps, on the hard metal scraps, and not other scraps. So this is very specific group, which contains the critical raw materials, tungsten, cobalt, tantalum, titanium, niobium. That's why it's very important, because they don't occur too often, especially in Europe. Our approach is to collect the scraps from the market, then segregate them and identify the composition of the scraps. We know how they are, because we've got the main manufacturers in our project, but there is a lot of other manufacturers also from China and smaller suppliers. So the collected scraps are very variable. So we're identifying what is composition of the scraps, not only in terms of composition of tungsten or other metals, but also the grain size, the carbides, and other factors. My colleagues are more knowledgeable in this field than me. I'm just focusing on something else. So this is very important, because we know what's in the scraps, and then we can process them accordingly. This is very critical, because when you downcycle the scraps, for instance, as a steel additive, because these are the techniques for today, we are losing the carbides. When you choke the titanium, let's say titanium carbide into the steel for high quality steels to increase the titanium level, then you lose the carbides, which is very high loss in terms of CO2 emissions and other factors. I don't know how I'm doing with time. Who's keeping the time?
3 minutes.
Okay, so I'm gonna speed up. Yeah, but this is very important, because that's the overview. So we are in terms of sorting of scraps. It's pretty difficult, because they are different shape, different size, different colors, different wear off. So we are implementing some artificial vision methods to sort the scraps. We are pretty good on that, and we can sort them as they are when they come to us after the collection. But then there is another step, which we want to implement, the sorting by coding. So we have some scraps already coded with some 2D codes, and we want to identify them by the code, and then to sort them accordingly with the higher accuracy, with the metal contents, grain size, and the chemical composition of the ingredients. This is very demanding. We are developing the methods for that. But next steps, after proper sorting for given groups, we can then recycle them in the best manner. The best manner means with less energy, with the best result, with recovery of most of the parts. And that's why sorting is very important, because we've got one company, Ticomet, who's now they changed the name, but I remember them by the old name. They can recycle them in very efficient way by the zinc recycling process, which takes apart all the tools and then leaves the powders intact, and they are very good for, let's say, recycling. It's a process, but for the reuse. Then we have also the other method, the parts which cannot go to zinc recycling, which is the simplest, the cheapest, and the less energy consuming. Then we can recycle the hard metal scraps by biochemical recycling. One of the partners is developing this method, and it's based on the use of biochemicals, which are not like a hydrofluoric acid or other acids. They are based on much more environmental friendly, let's say, ways to recover the materials in a good form from the very mixed scraps, which cannot go to the dedicated recycling. Then after that, We are reusing the powders acquired from the recycling, and we are making the new tools to verify their robustness, the quality, and the lifetime. So this is the full cycle from recycling to manufacturing of the new tools. And yeah, the project importance, what we want to do, and what we are achieving here is the let's say circular supply chain to avoid the downcycling, as I mentioned, to do not lose the metals and the compounds, the carbides into the steels. So yeah, this is the most important thing. And as a, let's say, summary, we can say that yeah, we want to make the whole circular value chain of the hard metals recycling in our project. So to have the Europe more let's say free from from external sources, and to increase the recycling in Europe, because in this case the values of the recycling of the hard metal scraps is pretty low, and then the export is coming out. So when we will show the demo products and the project results, we will be in a very strong position to increase the recycling and all the reuse of the materials that we already have in Europe. Yeah, so this will be about it. So, thank you very much.
We are on time. I don't know if we have time for a question. Maybe we can. Yeah, does Canal? You have a question? Comment. I should know everything.
Sorry?
You should know everything.
Just to mention as important point here, rather than scrap, we prefer to call it end-of-life products or secondary source materials, because this is one of the main barriers we encountered after we started the project. I mean, we collect these materials, we work on recycling technologies. Indeed, this is a project at a very high tier level with participants, very strong participants from the European industry, as you can see over there. But the problem is collecting scrap and moving it around Europe has been a big barrier. Therefore, the reason for that is when you talk about scrap, it goes into waste management regulations directly. So now what we're trying to do, in addition to what Jakub said, is we're trying to make a kind of simplification in this handling of end-of-life products or scrap, so that we are being more competitive with other companies out of EU. So that's something I would like to mention for RESQTOOL project. Thank you.
Yes, that's very important. Thank you, Kenan. I've forgot that we shouldn't be using scrap as a waste scrap. We should be using like a high-value secondary raw material. And this is important because, as you see on those pictures, these are the new tools, and these are the old tools, the wear-off tools. So the top ones probably doesn't really differ from the new ones. Yeah, they have like a 0.5 millimeter wear-off part, and that's it. Yeah, and they have to be recycled. So this is one of the things we are also encountering and trying to address, that this shouldn't be taken into account as a waste in the waste management system. It should be like a secondary raw materials. Thank you very much.
Okay, thank you, Jakub. Thank you. So the next talk will be from our co-host, Marko, who will also talk later. But now he will talk about the Bloom project. Let me go to the presentation.
It has nothing to do with vegetables or
plants. It might in the end
it might
improve. Yeah, where is the mouse now? Where is the mouse?
Disappeared.
Yes.
Jerry disappeared.
Maybe Tom's fault. Yeah. It's there. Which side? Ah, there it is. Yeah. So, yep. There we go. Marko, floor is yours.
Thank you. I'm going to present to you the project Bloom, which has started about a year ago, so we are still in the process of putting the things together. Anyhow, we have some initial results, and I'm just going to fly through them. Okay? So we all know the challenges Europe is facing. I won't go into details. We are all here to address those challenges and to try to find solutions that we can work on in the future. So based on that, the Bloom is aiming to facilitate the optimization of the process between the raw ore and the final outcome of the process comminution. And with that, we are trying to implement real-time technology that will optimize this process in a better way to produce the best possible outcome for further processing. The key objectives are to basically integrate the mineral liberation analysis with LIBS and with artificial intelligence, and to develop, like I said, a real-time feedback into the loop of the processing to facilitate it and to optimize it. We are aiming at the end of the project to build a sort of movable laboratory that could be shifted around the world in a size of approximately 1 container. And that's also a part of our project that we will test in Ukraine and in Canada in 2 mines. But of course, that will be then available when it reaches its higher technological readiness level to be shifted anywhere around the world and to be used also for other materials, not only those that we are focusing right now, which is tantalum, niobium, copper, and cobalt. Okay? And since we want to address the feasibility of this technology, we also are trying to assess its economical perspective, its economical visibility and size aspect, how to optimize it and how to make it attractable to the industry to be uptaken after the end of the project. So basically what we are trying to do is, I just put this scheme quickly together. Within each step of the processing of raw materials, we want to introduce the mineral liberation analysis, and that one will instantly give us the information how effective that part of the process is. And if it's effective, it will further go on into the next step. If it's not effective, it will return back and do the optimization of the process to get better results. So like I said, we have a long way to go, still a couple of years ahead of us. So we've now passed A and B, and now we are the requirement baselines. We already received some ores to work upon and to optimize the process of inputs to the algorithms, and then further on, when the system gets developed, it will be upscaled, fine-tuned, and put together in a whole technological outcome. So the first just came out of last week out of laboratories. These are the first results, the optimum grinding for specific minerals, which then enables the optimum outtake of the materials that you are looking for. How do we do that? Through the 15 partners within the project with different capabilities, different knowledge. And we, in addition to only 3 European countries, Spain, Portugal, Belgium, we have 3 non-European countries, which are the focus countries of critical raw materials strategy for Europe. And with that, I went through the presentation rather quickly to compensate your time and that the lunch will be on time. So any questions, I'm open.
Thanks, Marko. Very considerate of you. If there's any question or comment for Bloom, we can take it. Yeah, that's Jakub.
Just remember, I'm not a metallurgist,
and I'm not a chemical engineer. So I'm geologist by background.
Geologist, okay.
It's not my fault, right?
No, geologists are very, very important. The question is that, so in your project you want to like speed up and be able to scan the tailings or other resources in the like a massive way. Am I understanding correctly, or?
Exactly. Not only tailings, also the primary ore. So
the primary
whatever comes into it, the idea is to first start with the solids, and then also to introduce a potential liquids analysis in the next steps.
Okay, so it will allow not only like a functional from point to point analysis, but rather in the bigger scale for the evaluation of the mines or other projects.
Exactly, that's the point, to introduce it within the whole process of processing from ore to the final product, which then is served to, let's say, your industry.
Yeah, all right, thank you very much.
You're welcome.
That's Beate, okay.
Yeah, thank you. I'm also a geologist, so my question is on the mineral liberation analysis. So in your container, which will go around, will you include MLR or QEM scan? I don't know which kind of machine or equipment you will use, and then it will be totally automatized, or?
It will be automatized on site, but it will also be connected to the cloud information base or database that will be fed from all other trials or processing around the world. So it will basically share the information from whichever source we get to optimize the whole processes.
Because MLA needs a lot of sample preparation, no?
Yeah.
But it's not real time. I mean,
well,
almost real time.
Almost real time. It's better than to wait until the whole process ends and then you scratch your head. So, ooh, where did we go wrong?
Okay, thank you.
You're welcome.
So thank you, Marko, and we will see you later. I think while I search for the next file, I wanted to point out that the two projects are actually sharing the title, because you're working on the primary raw materials and RESQTOOL is working on the secondary raw materials. So that was the idea of the clustering, why we wanted to have both sides covered here in the session. So the next presentation goes back to recycling, and it's from EUROTITAN. So I'm opening it, and Rosanna can come and give a presentation, please. It's coming. Yeah, here we are. Rosanna, the floor is yours. Thank you.
Thank you. Hello, everyone. I'm Rosanna Babagiannou from CESLab, and we are here today with Beate Orberger to present you the EUROTITAN project. EUROTITAN is a Horizon Europe project that starts in 2024 and ends in 2028, and we are here to find the most decarbonized way from titanium extraction to allow Europe to be more self-efficient and self-sustainable in titanium chain. Our scope is to create TI extraction from two main metallurgical residues, from TI dioxide and alumina. And we are here to demonstrate the process in two pilot sites, in aluminum plant in Bosnia and Orano in France. EUROTITAN's solution is technical and systemic. Technically, we are finding new titanium extraction processes which are more clean and efficient, and systemically we are bringing together research, industry, and the whole process for a more clean and sustainable solution. Here we have the processes. The processes we are using in EUROTITAN. We are handling complex raw materials, and we are focusing on the whole chain from titanium production. But I'm here to present our big data platform, the digital backbone of EUROTITAN project. In our project, we created this platform to support all these processes and allow the data to speak itself. So we have in our architecture the data that comes from different sources and can give operators real-time analytics and predictive modeling. Our data visualization tool has key features that provides real-time and historical data, which is very convenient for correlations. We have modular widgets that help every user, from a researcher or industrial engineer, to have a clear vision of what's happening per process, and provide time series, key performance indicators, and the facilities map, which the whole process it's intelligent enough to give awareness from what is happening and prevent downtime and risk with color-coded real-time alerts from modules. So with red alert, we can see that something is wrong. With yellow, it's a warning alert. And with green, says that everything is going as supposed to be. We are providing also a data toolkit. A data toolkit, it's an after-processing toolkit. So once we have collected and analyzed the data, the researchers and engineers can see all the data in a way that they are wishing. So we have an AI prompt which allows the engineers to have advanced analytics per each process of the project, and have machine learning applications per each process and workflow. So we can predict models, create advanced analytics, and make decisions that will save our process time and forecast any problems. So what is the EUROTITAN's value proposition? EUROTITAN Big Data Platform, it's a scalable, it's AI ready, and we have worked to be intelligent, so we can semantically drive the whole infrastructure. We can handle the data in a federated environment. We can perform real-time analytics, and machine learning techniques give us the possibility to forecast problems and make us more efficient. And that's it from our side. Thank you, everyone.
Thank you, Rosanna. Yeah, clearly the data management is also very important for these new. Beata, yes.
Just want to add something.
Yeah.
Yeah, Rosanna has also a poster, and we have also on our results a session on Tuesday around 1:50 in the PM. So that is just.
Yeah, that's in the European because this is separated from them formally, but yeah, then I will change hat in a few hours. No other questions for Rosanna? No. Okay, thank you. Thank you. So next we are coming again to, of course, another project, and we're coming back to the rare earths because the project is called REESOURCE, and we have Duygu here, who is going to address you about the project in the usual 8-10 minutes. Thank you.
Yeah, hello everyone. I will talk about primary resources again, and it's very maybe exciting for all of us because I will be talking about rare earths in Europe, primary, hopefully. We will see. I will just talk about a bit like where we are using the rare earths, but I know that like there's a lot of industry players here also, like the magnet. This is a very hot topic. Even though it was not our primary idea to go to the end point of magnets, but it's very relevant for European industry. And then also the batteries and all other metallurgical, let's say, utilization of the rare earths, very motivative for us. I will talk about a bit the use case in our project. The fan complex located in Norway, as you can see, it's in the I don't know if you see my. No. Yeah. So it's kind of in the middle of Norway, the region called Telemark. So it's like, you know, in the Nordics we have a lot of indigenous population, especially in the north part. This is not one of these regions, but in Nordics we have very strict regulations for social impact and environmental impact. So this is one of the things that we take very serious in the project. And yeah, as you can see here, this is where the mine is located, and it's a kind of historical mine actually, where the iron dolomite relevant mining was taking place like years ago. So the population there is very used to the mining activities. So it helps a lot for generating the social acceptance for us. But the problem is that like this region is very, let's say, energy demanding region because of the new sites about like the data centers will be located there. So the population is a bit, let's say, concerned about the energy related issues. And then there will be a science park there, hopefully. So now the commune, the municipality is considering like where it should be located if there will be a processing plant. So basically, we have a lot of geologists here. I'm a metallurgist myself, but the geology of the area is basically carbonatite complex. And this carbonatites, and we have to some extent monazite, it's basically phosphate mineral. So it's basically a mixture, but mainly carbonatite. So in rare earth, primary rare earth processing, it is very important to, let's say, know what do we have and what is the grade generally, because it affects processing pretty much. And for fan deposit, the total rare earth grade, the oxide is between 0.5 to 2%. So when it comes to the resource objectives, basically we are trying to establish an invisible mining, responsible mining. That will be, of course, like underground mine. But we are also working on the backfilling of the tailings. So in our approach, there will be 60% of the tailings will be backfilled to the mine back. And then the rest of the tailings will be utilized in different applications. So as we mentioned, some challenges from the secondary raw materials, this scrap thing, we also have the same problem when we call tailings as tailings. So we generally have a tendency to utilize, or like, let's say, call them residue, process residues. It's better because then you have better options to utilize them in different applications and maybe set the regulations a bit, because we are talking about the Nordic environment where the regulations are very strict, maybe to some extent even stricter than European context. So when you call the tailings as tailings, then you have a lot of issues. But we set these ambitions ourselves that to more than 50% of the tailings will be backfilled. And now we are working about backfilling composition depending on the geomechanics of the mine, of course. And we are around 60% utilization, which is very good based on our expectations. And then, of course, the other part was the low hazard mineral flotation work. The issue with the railroads, to some extent, we have also the radioactivity coming along with the railroads. And this is very problematic because in Europe, we don't have this processing capacity and, let's say, experience that much, except certain very fundamental companies. But when you start, let's say, transfer the things like the concentrate, tailings, and the ore in Europe, then there will be a lot of regulations coming up, and then you need to deal with them. And we don't even know this kind of regulations. For instance, right now in Norway, we keep sending the materials between us, but then it comes radioactivity-related regulations, transportation regulations, and all other regulations. So we are now trying to figure out what kind of problems that we can face when we are working with the primary railroad in Europe. And then we are trying to, let's say, increase awareness for the policymakers so they can start dealing with it. Because there are some points that even the governments are not aware of it. For instance, let's say if you are working with primary processing, what about the underground water or the drinking water regulations? Have they ever measured these ones? Because when the company starts working on that, maybe there will be some questions coming up, even though there will be, let's say, no impact, right? So this is where we are working with the circular water management to setting the, let's say, baselines and let's say background measurements of the area, because we are talking about naturally occurring radioactive materials in this case. So these kind of things are very important. So we are also working about reducing of the water consumption from the mine to the processing plant also. And also, let's say, cleaning of the water and checking the underground water. And also, digital ventilation and airborne emissions control is also another important part, because then we are working with norm, and then there will be some additional, let's say, radioactivity-related emissions. Then this is where we control everything in a pretty much good way. And then, as I mentioned, tailings management and circular economy, backfilling, plus the additional innovative approach to utilize tailings part of these objectives. And then, of course, eventually, since we have the mine, we have the deposit in Norway, we are trying to generate a business case to make it feasible and, let's say, competitive to the extent. And the social acceptance, as I mentioned, is something that we give very, very much attention. From the beginning of the project, we had a lot of stakeholder meetings with the social community, the society there, to understand their concerns, because most of the times the concerns are not as expected. We are thinking about maybe the populations considering the radioactivity-related problems is the big issue, but this was not the case for that. Or the, let's say, acid related to mining operations, etc., the process reagent. But the society's, let's say, concerns were pretty much different than what we expect. And it's very important to us to understand and address their concerns, so we we are aligned and we generate social acceptance also. And for this part, we have social scientists working every day, daily, with the society. And then I think I mentioned most of the things here. So basically, we have the use case in Norway now, but we are also hoping to implement the similar solutions like raise mining, as I mentioned, raise mining operation to other European mines where we have, let's say, sensitive area or like very strict regulation areas like Nordics. We are open to, let's say, investigate the other use cases in Europe. So this is basically us. I think it's fine, and almost done. Thank you.
Thank you, Duygu. Any question on resource? Yes.
Yes. I don't know if you have mentioned what is the concentration of rare earths in the ore, and once the mine is open, what could be the annual outcome, and for how many years? You have an estimation?
Yeah, the average grade is somewhere between 0.5 to 2. It depends because it's a big area, and like it will depend, of course, like where they will try to focus. But the estimation is good enough to, let's say, generate a business case. Yeah, we can discuss the details in a, let's say, with the numbers like billion tons. Actually, it's pretty much a good. Let's say, deposit for Europe. It's very, very promising. And the grade is not, like it's, as I mentioned, it's somewhere between at least 1.7 in most of the regions, 0.5 to 2, but let's say. Yeah. Yeah, and especially imagine with the Nordic, let's say, standards, if you want to establish a mine and like operate it, you need to have very like a good baseline because it's very costly. Because of the regulations, you need to align with the regulations to even get a permit. It's not that easy, so the company is doing very good in this case, actually. Yeah.
Just a short question. You mentioned some concerns what the population had. Can you share some of the concerns they had? Because this is very interesting in terms of opening a new mine. Because we are thinking, okay, radioactivity, just like you mentioned. What did they are afraid of?
Yeah. I mean, surprisingly, we didn't receive any significant concern about radioactivity. This was very surprising for us because this is the general, if people know a bit, like this was the general thing. But they were more worried about their drinking water and the dust in the area. And like maybe some geomechanical changes in the area, like it happened in Sweden, for instance, like they had to like carry the whole area. But this was very minor things. In the area that we are talking about, the biggest concern is about windmills, for instance. This was also surprising for us. They are more worried about this kind of like disturbance, the bird population and different things. So the society there is very let's say having hopes about the mine. And also, of course, this also, let's say, bring some benefits that the area is a mining area already, like historical mining area, so they are used to. Yeah.
So, thank you, Duygu.
Thank you so much.
Thank you again. Yes, now, it was interesting this morning to hear that tellurium is considered a strategic material in UK. Because that's not the case in Europe. But this project that we are talking about is actually trying to overcome this issue. And Filipe is here to talk about START, which is actually there.
Yeah, okay.
Thank you, Filipe.
Thank you, Bruno, for the invitation, for giving this talk here on this workshop. And thank you all for your presence. So I'm going to give you some details about the START project. You have here the title already. So this is the brief outline of my presentation. So this is an innovation project that is coordinated by LNEG from Portugal. We aggregate, we are a multidisciplinary consortium. It was needed for implementing of this activity. So we include research organizations from different scientific domains, SMEs, companies, and also to non-profit organizations. So the project already started in 2022. It will be concluded next May of 2026. So what are the main objectives of the project and main goals? So we are transforming or converting mine waste into thermoelectrical materials in order to produce tellurium-free thermoelectrical devices. This is an important issue related with the thermoelectrical technology. I will give you some more details in the next slide. And with that, we expect to create a sustainable supply chain for thermoelectrical technology. With these objectives and the work that we are doing, we are promoting sustainability through efficient use of raw materials. We are reducing reliance on external sources, minimizing mine waste, and promoting the use of green energy harvesting through thermoelectrical technology. So, why thermoelectrical technology is important? So, these devices are solid-state devices that have the capacity of converting heat, what is called waste heat, and what is waste heat. For example, this laptop here is producing heat. So that is considered a waste heat. Many other industrial processes also produce waste heat. And we can use that heat that is not used and convert it into electrical power. And for that, we can make use of the thermoelectrical devices. So here you find the schematic representation of the thermoelectric model that is also highlighted here. It has two main components, which are the P-type and N-type thermoelements, which are semiconductor materials. So besides being solid-state devices, this type of devices also don't have moving parts, they don't produce noise, and also they don't emit greenhouse emissions. However, there are some limitations related with this technology. So they have a low efficiency for broad industrial needs and rely on rare and expensive raw materials based because they are mainly consisting of tellurium-based materials. The refined tellurium production is mainly concentrated outside Europe, mainly in China. So this represents a critical supply risk. For example, during this year, China canceled the exportation of that compound over there, the bismuth tellurite. So this is really an issue for Europe if we want to implement this type of technology here in the European Union. So there is a need to find alternative thermoelectrical materials in order to implement a sustainable development of the thermoelectrical technology and find alternative solutions. And in start, we are doing that by reprocessing sulfite-containing mine wastes, mainly those based off the tetrarite-based minerals, and converting those minerals into the P-type semiconductor materials. So we are combining natural with synthetic tetrarite to produce the thermoelectrical materials. With that, we are bypass metal recover. We are decifying the thermoelectrical materials solution, and with that also support the European autonomy related with the green transition and related with the thermoelectrical technology. Why tetrarite mineral? Because besides it has, of course, excellent thermoelectrical properties, and as you may know, it is the most widespread sulfur salt on Earth. For just to simplify this, here you can see the presence of the localities where the tetrarite subgroup is present in Europe. However, they are known as dirty concentrates because it contains some impurity elements that are problematic for the copper concentrate. So with that, it means that within the mine waste, we can find suitable and valuable secondary raw materials, like the tetralite is an example. And with that, by exploiting those waste mines, we can create and increase economic incentive to eliminate environmental problems related with the tailings. So here it is a schematic overview of the methodology that we are implementing. It covers different scientific domains that went from defining the possible locations for sampling the minerals, material processing, production of the thermoelectrical device, validation of those devices, development of business cases, studying environmental aspects related with the technology. And here are some of the results. So we have identified suitable localities for sampling these minerals in which is highlighted here on this map in Portugal, Spain, Germany, Austria, and Slovakia. But as we already understood here, so the regulations are different from country to country. And for example, in Germany, we were not able to sample any of the mineral. We only identified the potential locations where this mineral is present. So we have collected the mineral. We have produced around 40 kilograms of tetralite concentrate that was incorporated in the materials processing of the P-type semiconductor materials. We have used those processes that are there indicated, high energy ball milling followed by spark plasma sintering. I'm not going into details about these two technologies. But we were able to upscale these processes. So the high energy ball milling process, for example, we are at a pilot scale, which means that we are able to produce around 1 kilogram per batch per cycle. For example, for the SPS consolidation process, we moved from 1 pellet per cycle to 12 pellets per cycle. Regarding the materials properties that we are achieving here are compared with what exists in the literature, we achieve a very significant improvement. It is highlighted there on the green star on that diagram that compares with what is published. We are producing the devices for two different types of applications. We also are performing LCA and LCC analysis. The preliminary results regarding LCA are quite promising, as are indicated on that table over there. So the main outcomes before concluding. So we are converting mine waste into high-performance tellurium thermoelectrical materials. We are in some way unlocking new economic value from secondary sulfide resources, and we are promoting sustainable materials and energy technologies that we expect to drive economic innovation and to support a clean energy transition. And with that, we hope to also to shape or promote shaping the future of sustainable thermoelectrical innovation in Europe. But before I conclude, I was yesterday here in Glasgow making a tour to the city, and I went to a well-known museum here in Glasgow, and I found this painting. This is a challenge for you. Do you know what this means, for example? Anyone knows? No? So this is presented on the Kelvin Grove Art Gallery and Museum. So it represents the conflict that occurs on the copper mining in Buka Island near Papua New Guinea, between the population and the mining company and the authorities of those countries. So this means that was not a problem for the past. It is still nowadays a problem related with responsible mining, and also the importance that was already talked in the previous presentation about the societal engagement, which is a very important aspect. If you look also, there is this highlights here. It mentions the company that was exploiting that mine. Okay, so with that, I conclude. I want to acknowledge all the members of START for the implementation of this work. Thank you.
Thank you, Filipe. Any questions, comment on START? Yes.
Thank you. Excellent project. So I have a question for this tetrahedrite. It is maybe different in composition from the different sites.
That is an issue, but the process, here, okay. The technologies for processing the materials after obtaining the concentrate, specifically the high energy ball milling, has the capability to, that is not a big issue, okay? It does not represent a big issue because you can adjust the composition in that process.
And
it's more or less easy.
So will you process it by flotation or?
No, electromagnetic separation.
Electromagnetic. And tetrahedrite can also have very harmful elements like mercury, cadmium, and so on. So
yeah, but the concentrates that we have produced, those elements are within the limits that can be considered. Okay.
Thank you.
Anyone else? If not, thanks again, Filipe.
Okay, thank you.
We'll move to the next project, which is, yes, Christian is already coming here. It's another project where also PMA is involved, so I know this. So REPTiS, this is about, again, primary minerals and namely titanium. But Christian will tell us more.
A little bit more.
A little bit more, yes, we know.
Okay.
We don't have much time to go.
You have to stop me then if I'm talking too long. So, hello, you have heard about a lot of projects, so I will add one more. In this case, and as you see in orange, it's dealing with titanium. And the full name would be extraction processing of titanium. So in short, we are dealing with titanium from mine to product in the end. So we have the whole process in the consortium. And we started last year in September, so it's 1 year of project time now. Similar map you saw. In our case, it's a little bit from east to west of Europe in a short branch to north. And you see here some general data. The objective, I would say, for Europe are two things. One is to improve titanium, let's say, production from mine by energy, CO2 footprint, and so on. And the other thing is to have a mine more or less within Europe, what's also not so common for titanium in the end. And from the partner side, we are the partners are more or less from beginning from the mine. That's a mine in Ukraine, and the university I'm coming from is together with them from, we have 2 chairs involved for mineral processing, and then let's say from mine to concentrate, and from concentrate to powder is a second chair involved for non-ferrous metallurgy. And we have then the partners for LCA, IRIS, and so on, for characterization, and also partners for the part production out of the titanium powder gained in this project. Maybe I start some details shortly on titanium. This is for titanium because Europe is more or less regard titanium production, basic production not existing. In processing of titanium till ingots and so on, a little bit. So it's a metal which is also important as many others in this case. here only some numbers. And also if you're going to products, you see here different fields. Medical is one topic, but titanium is a relatively light construction material, can be used in different applications. The forecast is that it will grow, and if we have no raw materials, it was discussed already a lot today, so I don't want to go much into it. Also, it's located in the critical raw materials. So in this map, but it's a question then strategic or critique. Strategic also means more or less supply if we have it in or want to have it inside. Technologically, this is the old standard process how to get from the mine, from the ore to titanium, and in here there are some points, maybe. Because here we have chlorides and so on. So in the standard process of production of titanium, there are some, let's say, chemicals involved which are not so, let's say, healthy in this case, and also regarding energy consumption and so on. The new process is based on a patent by our mine, Welter in this case, and it avoids some solid waste and liquid waste generation, meaning we are using, and especially in our university, we are screening the raw material, which elements are in, how maybe they can be used for other products and so on. Also some maybe rare earths, not the heavy one, not neodymium, but maybe others. And so meaning we try to use more or less also discussion, no tailings. We have only one raw material and want to produce something out of it. But I think in every country in Europe that's a problem. Out of the past we are talking about waste, and we have to rethink there is no waste, there are only raw materials. And this has to be also, let's say, put into the laws that there is no waste, let's say it this way. Because there are a lot of restrictions only because of the definition of waste, what was already mentioned today. And I can, from my side, also stress this in this case. So we try with this process for maybe some more. In the topic, we have the calcination step to reduce out of the concentrate to get up to the titanium in the end. For a short comparison of both processes, the standard one, we try to have energy use, CO2 consumption, that's projected values, and also from byproducts and so on to really use as much as possible. One point out of my general, let's say, experience, the point also we heard now, the rare earth is maybe up to 2% in the, meaning you have 98% of others, and that's normal in mining in the end. Also, you have more gold in your mobile phones than in a mine, usually a gold mine. So that's a little bit, and if you're looking at LCAs and the raw materials included, then you see most of your impact in an LCA is the raw material. The rest you can do more or less everything a little bit over stressed now, but the raw material is really energy and let's say, and if not, let's say the energy consumption and CO2 footprint is in the raw material in the end. So we have to be aware. Then for our project, we want to improve the whole process, and especially because my university is involved here, and out of the first results we can say we have very challenging goals for energy reduction and so on, but this looks realistic in the end out from the first screening. So because one thing is that the standard processes for mining and processing are not so high sophisticated. So if you put in some more sophistication, it's realistic to reduce energy consumption and so on. So in this case, we could increase a big impact, and so we are very positive. With zero waste, it's always a topic, as mentioned, there is no waste. We try to reduce, let's say, what's left over as much as possible. Then some pictures from the mine side. Unfortunately, our professor was not traveling to Ukraine. We are doing this via distant contacts and so on. The mine is more or less in the middle of Ukraine, so not so dangerous, but you can be everywhere there and even in Poland, and it's not so safe. And also we learned a little bit how to transport concentrates from Ukraine to Austria. It was also some experience and took some months to find out how to do the administration and so on. So we have some of our own experiences here. Then the results, more or less, we really want to show that the production of titanium is possible, let's say, within Europe, and also that it's possible within, let's say, energy saving ways. And also, in this second part of the project, that with this powder we get out of the mine, well, concentrate in the end, we can really produce functional titanium parts in the end. So we have the partners in the project to do several, let's say, case studies or parts to show this powder is industrial use, so we can really have an industrial impact all together. The project wants to be together also with LCA. I forgot it's in parallel to follow it and to have the overall picture also, not to, because usually scientists are dealing with one topic and the rest has to be done by others, let's say it this way. So someone has to have the overview. But nevertheless, altogether, we want to really do, and it's, I would say, relatively industry-oriented from project side, to have really good outcome that we have titanium powder production here and titanium production in Europe. So it's, from my point of view, also regarding industry in EU, a good project to have a really industrial impact. With this, I say thank you for listening. Hopefully I was in time. So.
Thank you, Christian. Any comments, questions on REPTiS? Yes?
I think that the powder is done by a reduction process, right?
Calcium and, yes, out of the concentrate.
Well, two questions. How do you get the spherical shape? And if the powder is porous or is dense?
We are not so far in the moment to have the first powders out of this process. But as far as I know, the powders won't be spherical in the beginning. There could be, if necessary, a spherization step in. So okay. This is planned, more or less. And with porosity in the moment, we don't have the powder, so I cannot say.
Okay.
Yeah.
Thank you.
But maybe I can comment on this.
Yeah.
Yes, it's a regular powder, as they are already been tested even by present sinters, so they are not porous.
Okay.
We got very high density, so
okay,
I think it will be good. And yes, as you say, it can be spherized for the AM applications, for instance, for the additive and metal injection molding. Might even work with the irregular powders, apparently.
Okay.
Yes, Beata.
Thank you very much. So we are sister projects.
Yeah.
And my question is, are you in final, will you implement part of the processing in Ukraine and refine somewhere else, or everything in Ukraine? Or?
In the moment, as a university, we are dealing with Welter, so meaning the mine, so they are doing the more or less processing up to the pre-processing up to the, let's say, at least begin powder or concentrate. From the concentrate to the powder, they are doing in the moment.
And for the business model, what is the final idea?
Yeah, they want to sell the powder in the end for the business.
Ah, okay, they want to do it.
Yeah, yeah.
Thank you.
We might have Ukraine in the EU in the future, so that might not be a question finally. But they also have a subsidiary in the Czech Republic. Oh, so that was your point, yeah. So
just to answer your question, the business model is based on mining activities in Ukraine. Currently, it's a patented process by the Ukrainian company, but the goal is to make it an industrial scale kind of production unit in Czech Republic. So the mining will be in Ukraine, the processing will be in Czech Republic, that is in EU. That's the business plan.
For the business case. I'm more involved in the development.
Just for clarification, is the project in Ukraine is an existing mine? Or,
Existing mine.
And what is it, they are producing ilmenite or?
Ilmenite, yeah.
Yeah, so ilmenite projects in Ukraine.
Yes.
Okay.
Yeah, because ilmenite you have iron anyway, so yes.
okay, then thanks, Christian. We can move on. Yes, now it's the time for José Manuel, who is going to talk a more general, give a more general presentation, not related to a specific project, even if he has. So maybe you will mention something, but it's actually a review. So please, José Manuel.
Some kind of review.
Some kind of.
So please go, yes. Okay. Well, thank you very much, Bruno, for the invitation. And yes, well, my name is José Manuel Martín. I work in a research center in the north of Spain, in San Sebastian. And I am going to talk a little bit now about the recycling activities of neodymium iron boron magnets in Europe, which I think that is a topic that has been addressed this morning, and probably there will be other presentations related with that. So probably there will be some overlapping with the information provided by other speakers. I apologize for that. Okay. Okay, yes. Well, regarding the need, I think it's a pretty well-known topic. Light rare earths and heavy rare earths are among the most critical materials. And the point is that they are using in applications that they are using in many industrial applications, but in particular, it's expected that in the future, there will be used in the growing sector of energy generation of e-mobility. That's why there is a strong interest on the topic. Right now, the overall production, worldwide production of rare elements is dominated by China, which produce 70%. Those are all rare earths, not only what are used for magnets, but there are a certain amount that are used in other sectors. And anyway, China is the dominant country, but anyway, the situation is at least better than 10 years ago, where China produced 95% of these materials. With the time, people has opened mines in United States, Myanmar, and so on. So the problem of the supply is less critical. Anyway, the European Union still import 90% of its rare earth from China, most of them in the form of magnets. And the most critical point are the heavy rare earths, which are necessary to make high-performance magnets for high-temperature applications, because here we have only two sources, which are China and Myanmar. So the critical raw material has established three strategies, three lines to mitigate this dependency. One is to develop the domestic production, and here in the long term, there is an strategic project to open a big mine in Sweden that could cope with most of the needs of the European Union. The second line is related with the diversification of the supply. This can help, for example, for the supply of the light rare earths that we can buy now from the United States. In the medium long term, the European Union want to establish strategic collaboration with third countries that is going to help as well. And finally, we have the recycling that so far is very limited. We say that only 1% of the magnets are recycled. So basically, there is need for more research and more investment, but there are projects and investment ongoing, so those are ongoing activities. And in the midterm, it could be a significant, recycling could cope with a significant share of the European Union demand. So recently, the European Union has established 47 strategic projects, which are full-size industrial-scale projects. This is not research. This is just opening plants and facilities for the production of critical raw materials. There are 5 of these strategic projects that are related with rare earth elements. One is related with extraction and processing, 2 more with processing, and there are 2 focus on the recycling of these rare earths. And moreover, the European Union is opening as well projects in third countries related basically the extraction of these minerals. Apart from this industrial project, there are ongoing research projects, basically in the programs, but not exclusively Horizon Europe. Apart from the recycling project that I am showing on the screen, we have other projects related with mining, extraction, and with substitution of rare earths. I am going to mention only what I think are the more representative projects dealing with recycling that you can see in the screen. As you can see, well, they are innovation actions, which means that at the end of the project, we should achieve a maturity level of 6 7s. That means that for each one of the technologies, we should implement pilot plans. They cover a lot of different technologies. They go from the dismantling and collection of the magnets from the machines at the end of their life until the remanufacturing of new recycled magnets. In general, we are talking of significant budget between 7 and 15 million euros. Very large collaborative project between many countries all around Europe and many institutions. We have still manufacturing of magnets in Europe. It has been declining in the last decade because of the competition of China, but still we have maybe 10, 15 companies making bonded magnets in Europe, and at least 3 making sintered magnets, high-performance magnets. But apart from that, what we are observing is that thanks to this strategic and innovation project, private investment is coming in Europe, and you see here that new plants are opening now. And the first 3 will be working on recycling, and the second one, not sure, but probably they will be using primary resource. We have as well a research group in Europe that support this, the development of these companies, of these new plants. Some of them are quite old. They have maybe 30, 40 years. So there is a long tradition on research. And apart from, let's say, universities or research centers that work with samples that in many cases are in the size of the samples that they manage is less than 1 kilogram, we have now in Europe at least 2 pilot plants which are able to process from the strict casting material till the final magnets amounts of batches of 10 kilograms or this order. Well, the state of the art of the manufacturing of magnets is basically the industrial production on China. And in the last years, I would say in the last decades, we have observed 2 main developments in China that they are now implemented industrially. The first one is the introduction and serial in lanthanum, which has allowed to produce conventional magnets but cheaper, because we are removing neodymium, which is quite expensive, for cheaper rare elements, cerium and lanthanum. And the second one is the introduction of the grain boundary diffusion technology, which has allowed, first, reducing the amount of heavy rare earths that we have in the magnets, but secondly, to create all these new grades that you see, which are the most performant magnets usually required for electric vehicles, wind turbines, and so on. And for example, regarding this grade, it is very likely that they cannot produce by any European company. I don't think that we have at industrial level the know-how to make these advanced grades. So if we think on research and what are going to be the long-term trends, they are coming from the past as well. I will say that there are three interesting lines. The first one is the implementation, because basically what we want is to move this line horizontally to the right. That means increasing the coercivity without reducing the energy product of the material. And this will allow us to go to higher temperature applications without the need of spending more dispersion, more heavy rare elements. That is keeping the cost of the magnets. So there are, I think, basically three ways that people is investigating actively still to achieve these targets. The first one is going on studying grain boundary diffusion, not only using heavy rare earth compounds, but other compounds, basically metals with low melting points that sometimes they have light rare earths, but in other cases they don't have even rare earths, and they improve the coercivity. The second one is to produce powders with a lower grain size using basically two methods, which is the HDDR process and mel spinning. But later during the processing, you must be able to keep this small grain. And the way in which people is working is applying technologies of consolidation using hot deformation. And finally, the other line that is going to, where we are going to see progress is in the introduction of cerium and lanthanum, but with the idea of not, let's say, downgrading the properties of the magnets. We know that we can introduce large amount of cerium, up to 30%, without damaging too much the magnetic properties, if at the same time we are able to optimize processing and microstructure. So just to summarize, European is applying three ways strategy to mitigate our dependency of rare elements. There is not, so far, an easy solution for the dependency of the heavy rare earth elements. Recycling is going to be important. There are ongoing projects and even pilot plans to make magnets. We have detected some critical points. For example, the need of classifying the scrap properly according to the composition. Here, the idea of introducing the waste codes. The second one is the need of designing the machines from the beginning. So we take into account already the dismantling, which is called eco-design. So far, we don't have too much scrap in Europe. This is a problem right now, but we expect that with the development of e-mobility in the 10, 15 years, we will have large amount of neodymium iron boron magnets scrap. And for sure, we have a strong research group in Europe that can support the, let's say, re-emerging industry of manufacturing in Europe, but still, I think it will take some time until we catch up with China regarding the technology. So, well, thank you very much for your attention.
Thank you, José Manuel. Maybe a very quick question if you have, but otherwise, we move further. Or not. We'll stay on the topic of the magnets, actually, so there will be probably comments. Okay. Thank you, José Manuel. The next presenter is from France, is from R&I, so we are going again to a project, but also to an industrial partner. So, Alexandre, that's your turn.
Thank you.
Let me start it. And there you go.
Thank you.
Thank you.
So again, the rare earth and the permanent magnet with the Magellan project. So before deep dive in this project, and I thank José Manuel for the overview. Magellan project is one European founded project. 3 words, I would just make, use, and recover, 8 countries and 14 partners. But first, three statements. All magnets are not created equals. That's something you need to know. Magnets are everywhere, and pretty nobody knows. And 3, the supreme art of war, according to Sun Tzu, is to subdue your enemy without fighting. So now we can talk about Magellan. But before, this presentation will be very practical compared to the policy session held before in this morning. Magnets are at the very heart of domestic policy and politic attention at the moment. Reindustrialization agenda, resiliency agenda, circularity agenda. It's at the very heart of the energy transition. Clean tech are based on magnets for EVs and offshore wind. Techno and defense, robots, drones need magnets. And geopolitics. Xi Jinping and Donald Trump are talking about magnets. So now I'll move to Magellan project, which is, I said, 8 EU countries, 14 partners. It's founded by Horizon Europe. And it's a 36 months project. It's about demonstration. The consortium is there. Again, 14 partners and 8 EU countries for the value chain make, use, recover. So we have makers, users, dismantlers, and recyclers. About the challenges, the permanent magnets containing rare earth elements play a key role in the green transition. I just mentioned that in the opening remarks. The challenge, José Manuel and some others are mentioning that, huge concentration of magnet manufacturing in China. So huge concentration of knowledge and know-how in China. In the world, and for high-performance magnet, because all magnets are not created equal, 10+ company can achieve the high-performance magnet. 10 companies. Maybe 1 in EU. Maybe. We don't even know. José Manuel just mentioned that. 99% for EU, 99% of external dependence for offshore wind. 99%. I should add, as the American just mentioned, the American Geoscience Institute, that the US shake the ground, shake the market, and shake the timeline. So make, use, recover. That's the 3 words we use to define our project. Recycling and high performance at the same time. That's quite hard. We try to avoid downcycling. Use with high efficiency at every step, from design to eco-design. And recover, try to upscale and demonstrate the short loop recycling. Here are the 5 objectives. The near-net shape. That's the way to increase resource efficiency. Optimize the performance and recycling to reach the EVTM, electrical vehicle traction motors grade. It's all about demonstration to reach the TRL 7. And of course, the responsible sourcing to to demonstrate that there is also other benefit that can lead to non-price criteria to shape the market. And we are focusing on the magnet-to-alloy route to increase recovery of rare earth elements. To each of these objectives, we have key performance indicators. I will focus on the first one, increase recovery of rare earth elements. The KPI is to recycle over 70% of the elements contained in stream of end-of-life magnets and to reach the high performance grade that nobody or one company in the EU reach at the moment, incorporating end-of-life magnet at the same time. So we need to mobilize a lot of technology. So we use these levers so a broad of technology to push the limit of efficiency at every step. It's a kind of renaissance. We used to produce magnets, and now we need to relearn how to produce magnets. So it's a kind of renaissance. You rediscover the wonders of antiquities, and you translate them in our new age, new time, with more sustainability and public acceptances. So the magnet-to-alloy route in the value chain, so at the upper side of the slide, you have like the linear economy from the extraction mining to the users. And you have the backflow, the backstream, and we use the magnet-to-alloy after the characterization and sorting, extraction and dismantling, to be sure and to guarantee the high performance that EVTM and offshore wind needs. Because I recall, not all the magnets are created equal. The expected results are a demonstration of the technical and economic viability, a better, or let's say a less carbon footprint, over 50% reduction, and of course a circularity to enhance resiliency. And like any renaissance, it brings impact in scientific, standards, economic and societal environment. Again, thank you for your attention, and I hope that key message have been acknowledged. Thank you.
Thank you, Alexandre. Very quick one. We should be at lunch now, so. Is there anyone? Very quick.
Because I worked on such a project on discovery before. It finished in 24. And what kind of magnets are we using? All types? Small or big or whatever?
Neodymium iron boron. That's the most powerful on the Earth. And then after that, it's about grades. And we try to reach EVTM, electrical vehicle traction motors grade, and offshore wind grades.
Requiring materials.
Thank you.
So thank you again, Alexandre. Let's keep it for the round table. Can we? Thanks. Now it's time for Marko to step again to the stage for the other project that he forgot about. Oh yeah. You shouldn't. There you go.
Thank you. Okay, I'm really boring being all the time here. So I'll rush through. The lunch is ready. I've just checked and it's downstairs. It looks great, so I'm hungry. Okay, the next project, the second project that I'm gonna present today is Persephone. It has a Greek name because we have a Greek coordinator, and it's actually quite an interesting project because it deals with introducing a real mining robot, or let's say a fleet of mining robots, in the exploration and in the next step in the extraction of mineral deposits. Again, rationale, the same as with every talk, we won't go into it. It's the necessity that we need to address. Okay, that's all. So Persephone has quite a plethora of partners from the academia that is doing the research on how to optimize the movement of these robots and, of course, the development of them, to the end users, to the mines. And here we have the Cuprum from Poland. We have the, who else? Another project, so it's magnesium, yeah, Greek magnesium. And we also have the, let's say, the end users from the application perspective, which is Epiroc and Mine RP. So the goal is, and of course we have a variety of partners, including South African, and most of the rest of us are from Europe. The goal is to develop, first of all, like I said, the exploration robot, which looks like a dog. I have a video with me. I gave it to you on the stick, but you probably haven't downloaded it. Don't worry. If anybody is interested, I can show them later on. It's a small doggy look-like robot that has a exploration facilities attached to it. And in the second, like I said, in the second phase, it will have to be a larger because it will also contain the drilling facilities and sampling facilities. Now it's just remote sensing or detection facilities or elements. And of course, that is just one part of the project. The other part is how to feed this information that the robot is collecting, or the fleet of robots. The idea is also to make a group of them so they can communicate among themselves and to do various tasks within the mine, especially in the parts of the mine that are risky for humans. And that's the whole point, to go deep and to go into the shafts or let's say, mines that are risky for failures, that are flooded, etc., etc. So the next step is also to collect all this information in close to real time, hopefully eventually in real time, and to feed into a digital twin of the mine. So we basically produce some sort of digital replica of the mine where we have the instant information on the quality of samples, and that will basically then feed into the extraction process. And of course, that's another challenge that we are dealing with. And we just had last week the midterm review, which was appreciated a lot. And I didn't realize that there's another issue to this robot. The biggest challenge right now we have, it's movement issue and what happens if it turns over. So that's another challenge that they have to think of, how the robot gets back on its feet and continues the work. Not very common thing for a human to think of, but when you consider robot, yeah, it is a task that is quite burdensome. So going back to the project, statistics, it's a Horizon European project, but like every else here, it will end next year. The budget is quite considerable, and Lulea is the leading partner. And with that, I think what's happening? I'm pushing the wrong button. I'm pushing the plus instead of going further. So the paradigms are focused on the core topics of the project, so underground mines, autonomy of robots, in situ sensing, data integrability, and then at the end, modeling of digital twin. The benefits are various, from the most strategic ones for European Commission to the European Union, to the basic ones for the end users. And like I mentioned, next, well, the previous week's achievements that I can quickly summarize are: we've tested the drilling system, we tested in real environments, not only in the lab. The sensors have been improved, and that's really a big advantage from our Dutch colleagues. The data flow has been tested and it's been successful, and also the creation of the virtual twin or the digital twin of the mine has started quite successfully. And that's for now all, and thank you for your attention. If you have any questions.
Thanks, Marko. Persephone.
Persephone.
Well, yeah, let's leave it to the round table then.
Okay,
Thank
you very much.
Or the round table downstairs, I don't know. Right, so last but not least, we always say that, but that's correct, is Thomas. He will give the presentation about what is being done at Ionic Technologies, so still in Great Britain here. Thomas,
Great.
Floor is yours.
Thank you, Bruno. So my name is Thomas Kelly. I'm Director of Operations at Ionic Technologies, and I am cognizant of the fact that lunch is shortly to follow my presentation, so I won't keep you too long. But I will ask everyone in the room a quick question. Who has travelled here today from the UK? Who has travelled from the EU? And who's travelled from anywhere else? Very good. The more observant will note that I had my hand up all 3 times. And that is the reality of living in Northern Ireland. So I'm coming from Northern Ireland, and in NI, we are subject to European legislation as well as British. And also, we are now back in Horizon as part of the UK. We are part of the Innovation Fund group in Europe, but only by virtue of the fact that we as an organisation serve the whole island electrical network. Right? We are, in the United Kingdom, not part of CRMA, but earlier this year, Northern Ireland was included, and that was determined by the Department of Business and Trade, which is part of the UK. So if you're still following me, no. Right, so I guess what I'm trying to say is, going on from the conversations had this morning, we represent quite a unique proposition, I guess, in where we are in the world, because the Windsor framework does include Northern Ireland in trading of goods with mainland Europe. So it's an interesting place, certainly, to start a critical minerals recycling company, let's put it that way. So I'm going to talk a little bit about Ionic Technologies. And when Bruno asked me to come and speak at this session, I said, well, we're not really in Horizon, we don't have any European projects, and we're not really a cluster either. And he just said, come and say something interesting. So I'll do my best. So as you will know, I mean, this is kind of context which we've covered already. Our interest in rare earths and permanent magnets obviously is in recycling. We know that magnets are everywhere, wind turbines, electric vehicles. We know the heavy rare earth content is something that's subject to a lot of debate at the moment about how much is required, how low can we go in terms of heavy rare earth content. But we know right now, out there in Europe, either in the secondary raw material space or embedded in application, there is lots of rare earth material that will come to end of life in the next decade and beyond. And that is our target feedstock for our process, because we take magnets at end of life as well as midstream production material, and we can take pretty much anything with heavy and light rare earth content and recover that to produce high-grade separated oxides. So our product that we make is a rare earth oxide powder, and that is appropriate for use in the EVTMs, the electric vehicle motor grade of magnet. So I'll explain about how we're doing that through an actual project in just a second. but where we sit in supply chain and a kind of very crude analysis of long loop recycling and short loop. This is taken from Argus Media. We operate a space in supply chain. We've seen different versions of this diagram today. We operate in a space where we perform rare earth long loop recycling and then separation of rare earths to produce rare earth oxides, which can then obviously be fed through into supply chain to produce new magnets. Our parent company, Ionic Rare Earths, is a mining business. We have a mine in Uganda that is with mining license, but it's undeveloped as yet. The business is focusing primarily on Ionic Technologies business, the recycling business, and the reason for that is because of the rapid access to market the recycling presents. Obviously, mining will take decades in many cases to develop. Our technology is accessible almost instantly, and I'll explain where we're at in terms of our TRL journey in just a second. What we do with material, we bring it in, we digest it, we remove base metals. So obviously, everyone is aware that a great deal of the content of rare earth permanent magnets is iron. We'll take that out. We can also remove nickel coatings. We can remove various of the base metals that are present. We then produce a mixed rare earth oxide, which has to be very pure to go into our separation process, which is primarily, or the proprietary technology is solvent separation, but we would use the ionic liquid technology that the business was effectively founded with as an accelerant to that process, making it very efficient. And then we produce separated oxides. So we work very closely with Queen's University in Belfast. That is where the technology came from, and that's where our patents originate. And we're part of the Queen's University Ionic Liquid Laboratory Group, which is predominantly supported by petrochemical companies. We have a very different interest to those guys in terms of the application of ionic liquids. So the tech, and again, I'll explain a project that we're working on, which is hopefully of interest to this group in just a second, but the technology represents a step forward in terms of life cycle analysis. So in terms of the product carbon footprint of dysprosium oxide and NdPr oxide, you can see here that we present up to 61% reduction in CO2 embedded within the product, and that is a direct Scope 3 emission reduction. So that is directly comparable with material that is obviously primary sourced. So in the case of dysprosium, the comparator is ionic absorption clay sourced heavy rare earth. And when you put that material into a European-based supply chain, those numbers get better, because obviously once you start putting that material into an alloy manufacturer that uses European renewable energy and compare that to conventional material produced in China, you would expect that the CO2 embedded within the product at each stage in the value chain will improve. So obviously, with the well-documented benefits of recycling over primary source material, what we're now looking to do in terms of a funded project which is supported by the UK government is to put this material through a supply chain that can be commercialised and can be commercialised relatively quickly. So we have a project which has just commenced within the last couple of weeks, which we're very excited about. And it is a circular supply chain project which is broadly based in the United Kingdom, although we're relying on German support for magnet making. We will take material from every stage of the supply chain and we will recover the rare earth oxides from it, put that material through less common metals to make a strip cast alloy, which will then be fed into magnet makers to serve 3 OEMs in the consortium. And then we're working with EMR, which is a scrap business based in the UK with presence in the US and in Europe. And the intention would be that they have a process for liberating magnets at end of life, which then obviously we would take. And because we have a long loop process, the condition of those magnets really can be quite flexible. And from EMR's perspective, it means that they can do something, they can do any process really to get the magnets out as long as they can recover them. Because as we know, liberation of magnets is going to be a very challenging part of the whole equation in Europe. So we're very excited about this project, and in addition to the practical work that we're going to be doing, we're also going to get some support from British Geological Survey, who are the owners of the UK's critical minerals data, they will be doing life cycle analysis on the whole supply chain, as well as an economic analysis. So we will present to the OEMs basically how much this supply chain will cost to operate. So where this helps us to get to where we're going, we obviously are keen to commercialize the technology as soon as we can. So this project forms a step in our growth from where we currently sit in the middle, which is demonstration scale. We have a plant in Belfast which is capable of producing 10 tons per annum of separated rare earth oxides. And the intention is to build a commercial plant which is up to 400 tons per annum rare earth oxide capacity per annum. So we anticipate, obviously, a lot of the material that we recycle to come from European sources at end of life, possibly some material from within the supply chain itself, but then also we have in-country support from a number of different other nations as well, where there's lots of material currently available. And we anticipate more in the years to come. We like the city of Belfast for a number of reasons. As I mentioned earlier, we are kind of in and out of European Union, so we have the sort of dual market access. But critically, I think someone mentioned earlier the human capital in this whole equation. We have built up a skill set in Belfast where we have 15 people within the organisation who are all chemists and chemical engineers specialising now in rare earth recovery and separation. And we really want to build the capacity where those people are based. And then one other item that maybe escapes a lot of attention is that Belfast is a very large deep water port, which we'll be using to bring feedstock in from potentially from a number of offshore wind projects, which will come towards end of life in the Irish Sea and the North Sea as well. So there's lots of material that will pass through Belfast that we can recover and recycle rare earths from. So that's a whistle-stop tour of Ionic Technologies and what we're doing. Our Drive 35 project, the circular economy project. And we will be presenting a few times over the course of the next few days as part of the main conference next door. So if you want to learn any more, please do feel free to grab me and we'll have a conversation about it. But for me, that's everything for now. Okay.
So, any quick question or we just go for lunch? You're in the Middle Earth, right? You look like.
Yes. I would like to know if there is any lower limit of concentration of rare earth in your scrap to apply your process, and what could be as well the amount of liquid, for example, for lessivation that you have to use per kilogram of solid material.
Yeah, so in terms of the answer to the limit, there isn't really, we haven't found any material yet that we've come across which is beyond the limits in terms of what's recoverable. So obviously some of the different grades of magnets will have very low concentration of heavies in them. So we've been able to extract, in every case of magnets that we've recycled, be able to recover the heavies from them. The reason why the process that we have in Belfast is quite well scaled is because while we recover 10 tons a year of separated oxides, that's across two separate circuits. So there's a larger circuit which does a light to heavy separation, and then another circuit which does the heavy separation, which means that really there's no lower limit. When we scale, we will obviously have to factor in what size to build that heavy separation circuit, because obviously that will need to reflect the feedstock. So but there's also an appetite for mixed rare earth oxide separation, because there are groups out there who are kind of recovering the mixed rare earth oxide, so we can work with that. If I picked the sort of follow-up question correctly, it was about liquid. Yeah. We can have a chat about that afterwards. There's lots of it. I have to go into the process with you. which I'm quite happy to do, but I don't think everyone wants to listen to this. But yeah, we can have a conversation. I can explain how that works, and you get an idea for it. Yeah. Okay.
Great. Thank you. This closes the morning session.
Thank you. Thanks very much.
Actually, it's already 1 p.m. So. Thank you very much. Let's go for lunch. I think we should shrink a little bit the round table. Maybe we can be here around 2, right? Yeah. Okay.